Okay, so first let's begin taking a look at a typical network example. This is from a social network. There's a set of individuals, and if we observe their communications over, say, the time span of a day, we get a pattern like this. Now let's say this is going to be our example of what normal behavior looks like for this network. Now an example of anomalous behavior might be this kind of pattern, where there's a huge amount of communication going between two particular individuals who are part of separate communities. So there's normally not a lot of cross-communication across these communities, but we observe it during this anomaly. Now, this is an example of an anomaly where a local explanation exists for this anomaly. All we need to do to summarize this to our users is say, there's these two individuals, and they're communicating with a much higher frequency than is expected. Now, here's an example of another type of anomaly where there is no kind of local explanation. This is an example of maybe there's a particularly busy day. There's a lot more messages than average in the network, but they're kind of distributed across the normal paths of communication, and you cannot point at any particular person here and say that the anomaly resides with this person. Now, given the size of the kinds of networks that we normally deal with, this is from the Twitter network, if there is a local explanation for an anomaly, you want to provide that to the user, because that can give them important information about what exactly is happening with the anomaly. So the task that we are taking on is, given your set of anomalous graphs that you've detected, you want to determine if there is a local explanation, and if there is, you want to provide the subgraph that encapsulates the anomaly that you detected. All right, so the basic representation of a network is with a graph structure like this. We're using a weighted graph structure where the weight is simply the number of communications or interactions between a pair of nodes in a particular time window. Now, if you construct a graph for each of your time windows in a sequence, that forms the dynamic network. And then your anomaly detector will report any graph instance that it believes to be anomalous, anything where the structure deviates from what you've seen in the past. Now, the most common way to do that anomaly detection is with some kind of network statistic, which summarizes the behavior of the network in some kind of numerical fashion. Once you do that, then you kind of just look for outliers in the time series that you've produced. Now, what we're focusing on is, given the graphs and the times that are flagged as anomalous, we want to produce those local anomaly explanations. So basically picking out the subgraph of this network that best explains the anomaly that was detected. Now, the approach we take to doing this is with score decomposition. So many graph statistics are sums over the edges or nodes in the graph. So basically, while the total score is over the whole network, there's a natural way to generate a score over a single node or a single edge in the network, and that's with the component of this sum. And then by using this kind of local score, you can use that to visualize the edges or nodes that are the biggest contributors to the anomaly score that caused the network to be detected in the first place. Now, the exact algorithm that we use is first you need to apply your global statistic anomaly detector to the time series of graphs to identify which networks are going to be anomalous and which ones you're going to analyze. Then for each of those detected anomalies, you're going to create a ranked list of the edges or nodes based on highest contributor to the anomaly score to lowest. Then you're going to create a local explanation set, which is your visualization set. You're going to do this by starting to add the top ranked edges and then continuing to add until the sum of the local explanation is at least some threshold of the total score. And then when you do your visualization, the set in your local explanation is kind of the core anomaly, and we will also visualize anything that's adjacent to this core anomaly to give some context. So if this is the kind of ranked list you produced when you applied your local score to all pairs of nodes in the graph, you have some kind of threshold, everything above that threshold would be part of the core anomaly, your local explanation. And then since node I is part of this local explanation, if there's any incident edges to that to those nodes, that becomes part of your periphery. All right, so let's take a look at how you would decompose a really typical network statistic. So graph edit distance is a measure of the change between two different graphs. In a dynamic network case, you would apply this to your current graph and the previous graph to get a measurement of the rate of change that you're experiencing. And because graph edit distance is just a simple sum of the change in the weights on the edges that you've seen, the score for any edge is just the change in the weight on that edge. And because this is because this is calculated on two graphs as a rate of change statistic, during the visualization, we're also going to provide the visualization of the graph in the previous time step to show exactly what has changed. All right, so if you apply graph edit distance to an anomaly, and you can represent the ranked list in the form of a cumulative distribution over the scores. So this is just a cumulative sum of the anomaly score provided by each of those edges, and then the red line represents the threshold for visualization. Now, if you look at this, you might notice that this is actually a very uniform distribution. Most of the edges in this graph are providing the same amount of anomaly score as any others. Even the ones at the top of the list not providing very much more to the total anomaly score than ones much lower in the ranked list. Essentially what has happened here is that graph edit distance has detected a global anomaly rather than a local one. This is that example that I showed earlier where everyone in the network has produced a few more messages than normal. It's just a slightly higher rate of communication. And so since every pair of nodes is just a few more messages than normal, you can't really point to any set of edges and say this is driving the anomaly. So this is a case where this breakdown doesn't really provide you a very good explanation. So basically, while there are lots of statistics that can be broken down based on their sum, if your statistic is prone to detecting anomalies that are global to the network, that decomposition might not be particularly useful. And when you get a distribution of the score that's very uniform, that's the case where it doesn't work well. So what we did is that we applied multiple statistics, and we looked to see which are better at finding global versus local anomalies. And we, in particular, used two statistics which are designed to find more local anomalies. So apart from graph edit distance, we also used Barat clustering, which is a weighted clustering coefficient measure, and also these two statistics which are called size consistent statistics, which we introduced in another work of ours. These are both mass shift and triangle probability. Now these are designed to be insensitive to the case where the communication frequency on average has gone up, but the pattern of communication has stayed roughly the same. So these tend to be better at finding more localized anomalies than other statistics. Now, mass shift is an analog for graph edit distance in that it's a measure of the rate of change of the network, while triangle probability is an analog to a clustering coefficient measure because it measures propensity for triangles. And if you take a look at how the cumulative score distribution breaks down for mass shift versus graph edit distance, you can see that mass shift is a lot less uniform in terms of the anomaly score. If you wanted to grab a subset that explains, say, 80% of the total anomaly score, for mass shift you can do that with a handful of edges. To do the same with graph edit distance, you'd need thousands of edges. All right, now let's take a look at some of the real-world data experiments we did. We used two main data sets, the set of email communications from the Enron Corporation, and also a set of Facebook wall postings taken from Purdue University students. The approach here is that we ran the global anomaly detector to find all the anomalous times in the sequence. For the anomalous time that produced the highest score, we did the decomposition and the visualization. And then I'm going to provide you what those visualizations are. Okay, so if you apply mass shift to the Enron data set, it identifies this particular time step, where there's a massive increase in the communication between these two individuals. Likewise, when you apply it to the Facebook data set, it finds a similar kind of anomaly. There's a pair of individuals who had a massive increase in their number of communications. And if you look at the actual content of these Facebook communications, what we found was that the pair noticed that they were approaching 2,000 posts on each other's walls. So they decided, well, we're going to reach that threshold in a single night. So they just kind of spammed each other with hundreds of messages until they hit 2,000. And they were very excited about reaching that threshold. But yeah, so essentially they went from just having a few messages per day to having like over 100 in a single night. All right. Now, in contrast, if you apply graph edit distance to these networks and decompose their anomalies, this is what you find on the Enron dataset. Now, when you take into account the core anomaly in red and the periphery in black, this essentially incorporates every single node in the network into your visualization. Now, with Enron, that's small enough to do that, but with a bigger network, you'd be in trouble. You'd want a visualization with a lot fewer proportion of the nodes of the network. And it gets even worse if you look at the decomposition on the Facebook dataset. So again, this is another case of that anomaly where there's just there's a higher rate of communication than average, but is very evenly distributed across the network. Even if you pick out the highest ranked edges and visualize them, it's not very much different than just a random set of edges in the network, so you're not really providing any useful information by this decomposition. Okay, so if we look at what triangle probability finds in the Enron network, it identifies this set of communications. So this is basically the members of the Enron legal department, and it found a day where, a time when they had a very high rate of communication between the members. Now, what's interesting is that Barat clustering also identifies members of the Enron legal department, but it picks a day where there's actually not a lot of communication going on. And this is because Barat clustering very highly penalizes communications that go outside of the local triangle or the triangular communications. So it prefers triangles that are on their own, even if the actual amount of communication on those triangles is not actually very high. Okay, then if you apply triangle probability to the Facebook data set, you find this particular cluster. And when we took a look at the content of these messages, it was actually a trio that were discussing Tiger Woods' odds of winning the 2007 Open Golf Championship. However, if you do the same for Barat clustering, again, it does find a triangle, but it finds one that's very isolated and doesn't have a lot of weight on those edges. When we took a look at the content of these messages, essentially there was no common theme to them. All right. Now, in terms of future directions, for this work, we've just had a handful of statistics, and we've applied them in isolation. You can imagine a scenario where you might want to identify anomalies based on a multitude of criterion. And that's straightforward to do with the decomposition approach. You just have to normalize and then break down the summed cumulative distribution, and then do some kind of visualization that takes into account the different anomaly types. Also, we focused mostly on the edge breakdown on the decomposition, but as I mentioned, node is possible, and you can also decompose by larger components. Like graph edit distance is easy to do with either edges or nodes. Clustering coefficients naturally break down by triangles, and you can imagine doing the decomposition by larger subgraphs of the network. All right, in conclusion, we demonstrated this method of decomposing a summed statistic in order to find local explanations for the anomaly. However, we showed that not all statistics that decompose provide good local explanations. You want to avoid using statistics that find global anomalies. And we also demonstrated that the two statistics that we introduced in other work are pretty reliable at finding good local explanations of anomalies. All right, now are there any questions?
Thank you, Timothy. Questions?
Did you consider looking into identifying whether there was a global anomaly or a local anomaly, and if in the case of global, just not even visualizing anything, just saying, there's nothing we can show you?
Yeah, that's basically what you have to do. What we did is we did the visualization for all the graphs that we found, and then sometimes we'd find a global anomaly where that visualization just wasn't useful. Basically, what you have to do is if you look at the cumulative distribution, you can kind of tell just by looking at that whether or not the visualization is going to be useful or not.
Other questions?
The first slide you showed this general stable neighborhood of a node and how they interact with them, right? And then how
Yeah.
it changes. But most of these measures, usually what they do is they compare to the previous snapshot, right? So if we want to really find a stable expected neighborhood of some sort, how would we go about thinking about it, and how would we change these scores?
Yeah, so you're right that the rate of change statistics I kind of used are really very local changes. It's the immediate prior to the immediate current. However, what you can do is kind of generate an average version of the graph from multiple past instances. It's especially easy with a weighted graph. You just kind of average the weights across the edges that you've seen in a certain time window. That gives you like the average set of communications. Then you just measure the delta from your average to your current.
Question.
Hi, I was curious if you considered with those global changes, identifying what they were, so did you consider like running it through some other system to classify the types of shifts you see? So when you see a global shift, you might know that, for example, some world event is happening or something else.
Yeah, the global event I described was an increase in the average frequency of communication. You could imagine having a different anomaly detector that measures just what is that average, and is that average deviate from normal, right? In which case, once you've found all the anomalies regarding average communication, maybe you don't look for anomalies on them with other statistics, right? The issue with that is that sometimes maybe there is another type of anomaly embedded in that kind of change of message frequency anomaly. You still want to look there, in which case you do need statistics that are kind of insensitive to that global anomaly that's happening at the same time.
One last question from that side. No? All right, so just in the interest of time, thank you, Timothy. And up next.